All right, so for today's lecture, we're going to talk about 3.1, the least squareless problem. Essentially, up till now, we've only talked about square matrices, and that's not everything, right? We can talk about rectangular matrices, but where does this kind of problem come up? Well, often you have more data than you have variables. So for instance, say you're doing an experiment and you want to relate two different physical quantities, say pressure and density. And if you want to do this, you may do an experiment 500 times, and but you only need to relate two variables. There's a lot more data than you have information that you are trying to find out. And so you might expect, say, pressure and density to have a linear relationship. And so let's say you want to find AI such that d of p is equal to a0p plus a1. We want to say that pressure, or density, is a linear function of pressure. And, this is a perfectly great problem, but if you have 500 data points, it's a lot more than you can use to directly find a0 and a1. Let's do an example. Let's say for a second our data is 1, 2, 2, 3.1, and 3, 3.9. Just do 3 points to be simple, right? So then what we want to solve, what we want to show is we want 2 to equal a0 times 1 plus a1, 3.1 to equal a0 times 2 plus a1, and 3.9 equal to a0 times 3 plus a1. So we want to be able to solve this system. Now, we have more equations than we have unknowns, and so we can't necessarily solve it, right? Let's look at this as a matrix. So we 1, 1, 2, 1, 3, 1, a1, a2 equals 2, 3.1, and 3.9. So we have this, this system. And again, not square, and this is a perfectly reasonable thing, right? Now, why would you expect there not to be an exact solution? Well, there's, how do I say this? There's experimental error. When you're finding this data, you might expect the answers to be 1 and 2, 2 and 3, and then 3 and 4. In fact, I kind of set it up to look that way. But in an experiment, you're going to get error, and so you just try and take your data and try and fit a line to it as best you can. All right. So what do we mean by fits as best we can? Well, we want the error to be small. And well, what do we mean by error? Well, let's call R equal to di minus d of pi. So here we have pi, di are the data. Say that pi is the pressure, di is the density. And d of pi is our model. It's our, say a linear function, right? We want this to be as small as possible. So, this is, as you may recognize, this is the residual. And really, if you think of it in the matrices that we just talked about, this really is b minus a times x if we were thinking about this as the normal matrices that we've been working with. So, we want the norm of R to be small. The norm of these residuals, we want this whole thing to be small. Now, we could of course choose any norm, and in the end they're all equivalent in some sense. But the theory works the best, and this is what everyone always does, is it uses the 2 norm. The reason why we use the 2 norm, well, that's not necessarily obvious, I guess. So this is what the 2 norm is, just to remind you. You square the elements and you take the square root after you add them together. And we want to make this as small as possible. Now, this is where the term least squares comes from, because we have something that we're squaring and we want to make it as small as possible. No one ever said that mathematicians were good at naming things, or inventive. Anyway, so this is what we want to do. We want to make these residuals as small as possible. So let's draw just a really quick picture. Here's D and here's P. So our data might look something like this, right? We have some points, and they're not all on a line, but we think they should be almost on a line. And so what we can, the least squares solution might give us a line that looks something like this, and then the residual is the distance between the point and the line. And that, given the formula that I just gave you, that's exactly what you're measuring. All right, and we want to make these as small as possible, which makes sense, right? We want all of these x's to be as close as possible to the line. Now, obviously, we're not expecting all of them to be on the line, or in fact, probably any of them to be on the line, but we can help, right? All right. So, I should mention that this is not only used for linear. Essentially, anything you want can be thought of this way. Any model you come up with, essentially. So, you can use any basis you want. So you could think of, for instance, maybe you think that density is a quadratic function of pressure. So you have a quadratic function over here, and this is your model. Well then, if we were doing the same kind of work that we were doing before, this is the equation that we get. We get A0, A1, A2 equals 2, 3.1, 3.9. Right, so this makes sense because if you take 1, 1, 1, you multiply it, right, you get 1A0, 1A1, 1A2. This is the P equals 1, P equals 2, P equals 3 equation that we got here. Now, because I only had 3 points of data, this ended up being just a square matrix. You could just solve it. But you can imagine that you would probably actually have, 50 or 100 or 1,000 data points instead of just 3. This was just for simplicity. So this is just marginally more general. You can go even more general than this. How do we do that? Well, you can say d of p is equal to, say, the summation ai pi of p, I equals 1 to n. And then we can do the same problem. Phi's are just any function we want. They could be, like we did before, they could be p or p squared, or they could be something more complicated like e to the p, or some, exponential or logarithm or whatever you want. And so there's lots of, you can do whatever you want. So in the end, for this kind of problem, we're going to get an n by m matrix with m unknowns and n equations. There's m unknowns, n equations. So because there's because generally speaking, we are thinking of n as being bigger than m, more equations than unknowns, we say this system is overdetermined. How I think about that is each equation should if things work out nicely, should determine one variable. And so if you have more equations and variables, you're over-determining what those variables should be. All right. So again, what we're trying to solve right now is the least squares problem. We're trying to find the AIs that minimize the error of this model. All right, so now of course the question is how to solve it. So sections 3.2 through 3.4 give a particular way of solving it. We'll talk about those on Monday and Wednesday. They're a little more complicated, but they're better for various reasons. There's some trade-offs involved. Let's go to 3.5. Let's talk about geometric methods. Now, of course, what we're going to be doing on Monday and Wednesday are geometric methods also, so this is not really new. Or this is not really different in that way, but whatever. So in this section, in 3.5, there's a lot of technical linear algebra tools. And you may not remember all of it, you're going to probably need to review it. The section is a good place to start if you don't. And also, I'm going to assign a lot of problems with some technical things that I'm not going to have time to talk about here. It's unfortunate, but I'm simply not going to have time to talk about them. So, but let's start out again with some technical tools. So let's let S be a subset of Rn. And so, just some vectors in Rn. So, and then the orthogonal complement of S, which we'll call S perp for perpendicular, is all the vectors perpendicular to S. This makes sense. S perp is things perpendicular to S. Excellent. If we want to write this out in set notation, we say X is in Rn, X at Rn is in our set if X comma Y equals 0 for all Y in S. So again, S perp is all vectors that are perpendicular, the inner product is 0 for all Y in S. So clearly we have the 0 vector is an element of S perp because the inner product of 0 is always 0. That's easy enough. So one important thing to say is that S perp is a subspace. Even if S isn't a subspace, S perp is. So a subspace just means that if you take two things in it and you add them together, you're still in the space itself. Also, if you multiply, if you scale a vector in it, it's still going to be there. And that makes sense if you think about this definition. All right, so let's go on. So the first thing, the first theorem that we're going to have here, the first tool, is that we're going to essentially decompose Rn into two different subspaces. In the book, this is 3.5.3. It says, if S is a subspace of Rn, this is a subspace now, not just a subset. We need it to be, closed under addition. Then for any x in Rn, there are unique S in S, and then S perp in S perp such that x equals s plus s per. So, again, what this is saying is any vector in S, or sorry, in Rn, any vector in Rn can be decomposed, can be split into something in S and something in perpendicular to S. And this is a unique thing, which is important. This is a unique decomposition. And so we say S is the orthogonal projection of X onto the subspace S. Essentially what's happening, if you think of this in 2 dimensions, you know, here's your vector X. You're saying, okay, well, let's project it down onto this vector and then project it into the perpendicular part. And so X is this plus this. Makes sense. All right, so something we should say is because this decomposition is unique, you can write this in a unique way. We can say this, there's some notation that you should know, especially if you're a math major. If you're not, it's not quite so important. So this symbol right here is a circle around a plus sign. And it is called the direct sum. So if you ever have a vector space or something like, yeah, if you ever have a vector space, and you split it into 2 separate pieces so that each element in here can be, you know, something in here plus something in here in a unique way, that is called a direct sum. And usually speaking, these are important. These are, you know, important, cool things you should care about if you can do this. All right. So, the next thing we're going to prove is a simple lemma. And this is really the Pythagorean theorem, which you learned in middle school or whenever you learned it. And in fact, it's even easier to prove here because we now have inner products. So, if U and V are orthogonal, if they're perpendicular, in say Rn, then we have U plus V, the 2 norm squared, is equal to the 2 norm of V squared plus the 2 norm of U squared, i.e. A squared plus B squared equals C squared. Pretty straightforward. So the proof here is really easy, so I'll just prove it. This is equal to inner product U plus V with U plus V by definition. If we do if we FOIL this out, we get UU plus UV plus VU plus VV. And this is 0 because they're orthogonal, right? And then this is the same as this, by definition again. So we're done. The Pythagorean theorem is really easy to prove if you're thinking about vector spaces. Whew. All right. So let's talk about something now, something else. I want to go back to the least squares problem for a second. So, let's say we have an overdetermined problem, AX equals B. Then, the least squares problem is finding x in Rm such that b minus ax 2, the 2 norm here, is the minimum over b minus aw. So again, this is the minimum of this quantity. This is the residual, right? So we want to minimize this. That is the definition of the least squares problem. And so this is, if we're taking the minimum, this is the smallest that this quantity can get. We're saying we solve it if we can find x that makes it the smallest. This makes sense. So, but there's another way to say this. Instead, we can say that we want to find y in the range of A. Remember, the range of A is just the things that if you multiply, is the things you can get out of the operator A. I'll show you in a second. So we want to find this such that b minus y 2 norm is equal to the minimum of s in the range of A, b minus s 2 norm. So this makes sense because here we're just trying to minimize this over everything, all the x's and w's. But if we instead do this, if we say y has to be in the range, well, ax had to be in the range of A, obviously, because it's A times something. Same thing with AW. So we might as well just say, well, let's take things over the range of A instead of over all of things. Just makes it a little simpler. All right. So, of course, so I mean, really we're just saying, again, ax equals y in like the very literal sense. And so, how to find this y, that's what we're going to talk about right now. So let's erase this. All right. Book calls this 3.5.15. So we're letting S be a subspace of Rn. Let B be in Rn also. Then there exists a unique y in S such that b minus y2 is equal to the minimum of S in S, b minus S2. So this is exactly what we wanted to show. If S is a subspace, so for instance, if it's the range of A, then there exists a unique solution, y in S, that's going to minimize this, this quantity, minimize the residual. All right, and what is y? Of course, if this is what we want to be able to calculate it. Well, y is the orthogonal projection of B into or onto S. All right. Y is the orthogonal projection of B into S. And that's how we're going to minimize this thing. So the proof is not too complicated. It's not too hard. So let's do it. So the first thing we're going to do is we're going to use the direct sum decomposition that we mentioned earlier. So let's split B into y in S and z in S perp. So we have b equals y plus z. All right. So then for any s in S, notice that b minus s is equal to b minus y plus y minus x. All right. So this first part is the direct sum decomposition that we mentioned earlier. It's just straight up that. And for any s and s, this is just adding and subtracting y. Now, why did we do this? Well, it works out that this is an s. Y minus s is an s because both y and s are an s, and it's a subspace, so they have to, when they subtract them, it's still an s. B minus y, on the other hand, is in S perp. And why is it in S perp? Well, b minus y is just equal to z. And z, by definition, is in S perp. So we're good. So why did we do this? Well, this is going to let us use the Pythagorean theorem on this. So, Pythagorean theorem, we have b minus s, remember we split it up, and so this is going to be equal to b minus y squared plus y minus s 2 squared. So, this is what we want to minimize, right? This is the residual. This is the quantity we want to minimize. So we want to minimize this, is one way of thinking of it. And the important thing to realize here is, as we change x, this is constant. B minus y can't change. Obviously, it's not going to change because there's no s in it. But this, y minus s, the norm of that is clearly minimized when y equals s, which is okay, remember, because both are an s, in the capital S, so they can be equal to each other. And so this is going to be 0, and this is going to be the same. And that's obviously going to give us the minimum. And remember, we defined y to be the orthogonal projection of B. And so, because it's the orthogonal projection, and the orthogonal projection is what gives us this to be the smallest, we're done. That's what we wanted to show. All right, so, that, while that theorem is correct and all, it doesn't look exactly like what we wanted. So I'm going to recast it a little bit, say it a little differently. Wow, I can't write it. Try this again. Corollary. Corollary is just an easy proof. And it's something that's easy to prove once you have a big theorem. So let's let x be an Rm. Then we can say that b minus ax 2 norm is equal to the min of w in Rm of b minus w 2 norm if and only if b minus ax is in range of a perpendicular. So remember, this is essentially the theorem that we just proved. Here, instead of saying y and s, we're saying ax and aw. And the space that we're using, instead of s, we're saying the range of a is the space that we're talking about. because that's all we can get out of AX and AW anyway. And so, why is this? Well, this is this AX is equal to the Y that we found earlier. It's the same thing in the two different proofs. And so remember, B minus Y is equal to Z, which was in S perp. But remember, we're talking S is the range of A, and so B minus AX had better be in the perpendicular range of A. So this is the exact same theorem, it's just speaking it in different terms. All right. So, now, there's lots of things, as I said, there's lots of linear algebra proofs that I'm not going into right here, but there's one in particular that I need to mention that's important here that really you should prove, you should go back and you should prove it and look at the proof and things like that, but I don't want to spend the time here doing that. So, that's this, theorem 3.5.10 says that the range of A perp, the perpendicular complement to the range of A, is equal to the null space of A transpose. Now, to remind you what the null space is, the null space is simply the vectors such that A transpose X is equal to 0. So this is not an obvious theorem by any stretch. But it says the orthogonal complement of the range is the null space of the transpose. It just happens to be true. You can prove it. It's proven in the book. It takes a little bit of work. All right. Well, here we know that B minus AX has to be in the perfect range, which means it also has to be in the null space of A transpose. So this means that A transpose B minus AX equals 0. This has to be equivalent to solving the system, solving the least squares problem. So let's write that down in the theorem. All right. Last theorem. .5.21. So let's let X be an Rm. We would say X solves the least squares problem. AX equals B. If and only if A transpose A times X is equal to A transpose B. And what's so cool about this is that A transpose A is now an M by M matrix. This is an M by 1. This is an M by 1. And so we can solve this normally. This is now a square matrix, generally speaking, not going to be singular. You don't expect this to be singular. And we can just solve it using the methods that we did before. So this is a great method. This is called the normal equations. Not quite sure why it's called that, but it is. And this was used for a long time as the main method of solving these problems, until like the 70s or things, and it's still used today, some at least. So there are some advantages, and first of all, it's simple. All you have to do is multiply both sides by A transpose, easy to do, and then just solve using our favorite method for solving the system that we're talking about. Also easy to do. it's also generally very inexpensive. The reason it's inexpensive is we generally think that x, the dimension x, so m, is going to be quite small, right? We're only solving for 2 variables in the pressure density thing that we said originally, maybe 3 or 4. Generally speaking, this is not a billion, right? Like some other problems we might solve. And so the most expensive part is calculating this product, A transpose A. But once you have that product, then it's a very small system. You say a 2 by 2 matrix equals a 2 by 2 matrix, or 2 by 1 matrix, which is very easy to solve. So that makes it very inexpensive, at least as far as long as you do this multiplication. So I did mention that this is not necessarily the main used method anymore. And the reason why is the method that we're going to be talking about on Monday and Wednesday, the QR method, QR decomposition, has fewer round-off errors. It just turns out that if you pick bad matrices, say usually ill-conditioned, but maybe some others too, then the round-off errors here with this method could be quite large. And I'm not 100% sure, but I think it's essentially because you're multiplying these 2 big matrices and you're losing information because you're adding up and subtracting lots of things. Don't quote me on that. But in general, that's the problem with this method, is numerically it doesn't behave as well. It's not as numerically stable as the QR method. Anyway, that's all I wanted to talk about for today. I think this is a little short, but that's all right. All right, thank you.